Thanks a lot, Professor Mike Wakin. Go ahead, the floor is yours.
Thank you very much. Just to confirm, can you see my slides okay? Okay.
Perfect.
Great. Thank you so much for the invitation, and thank you everyone for tuning in today. It's great to have this opportunity to reach you with Zoom. My background is in signal processing, and generally speaking, I look for ways of characterizing mathematical structure in signals and taking advantage of that structure in order to simplify, make more efficient the acquisition and the processing of those signals. To date, much of my work in this area has been in the domain of compressive sensing, where we typically use low-rate randomized sampling schemes to capture signals with the plan then of filling in the blanks algorithmically based on what we capture. Today's talk, I will start with a high-level overview of compressive sensing in the first few minutes before transitioning to the specific mathematical problem of today's talk, which is modal analysis for applications, say, in structural health monitoring. But the particular problem we'll consider within modal analysis is how to successfully accomplish that when we only have a small number of random or compressed samples of the data, and how that leads to efficiency and what sort of mathematical guarantees we can establish for solving those problems. So I'd like to acknowledge a number of collaborators with whom I've done this research. And at a high level, our research is motivated by the challenges of doing signal processing in the big data era. You know, we now have the opportunity and also the charge to capture ever larger signals and data sets, ever higher resolution images and video. And this presents a number of challenges in the complexity of the data acquisition process and the subsequent storage, transmission, processing, and analysis of all of that data. And so to combat these challenges, we look for some opportunities, and a major opportunity that we can often take advantage of is the observation that not all signals are created equal. You know, an arbitrary or randomly generated image might look something like the one on the left of the screen here, but a real world image typically looks something more like the one on the right here. And if I were to ask you to describe what you see in the image on the right, you would be unlikely to just step through each pixel individually and tell me what you see, but you'd be much more likely to describe the objects that you see and their orientations and their positions and some other characteristic features. And after a while, probably not using too many words, you'd be able to paint a pretty good picture of what you're seeing there. But really the information level, kind of the number of words or parameters you need to describe what you're seeing in the image on the right would be far smaller than the number of pixels in that image. So structured models may be able to characterize the structure or the information of a signal or an image using far fewer parameters than there would natively be pixels or samples in that image. And that presents an opportunity for capturing or processing these signals and images much more efficiently than without exploiting these models. So to dive in on that a little bit, let's talk about sampling. So suppose we have the blue signal here and we wish to sample that signal, acquiring the red samples. The fact that signals often obey structured models means that once we acquire these red samples, you know, maybe at the Nyquist rate, so that is, Nyquist rate says whatever the highest frequency in the blue signal, we should sample twice that fast to acquire the red samples, and then we lose no information. That's true. But there may still be some residual structure. And with that residual structure, you could then exploit that. You could do things like compressing the samples. This happens a lot in image processing. This is what happens when people do JPEG-based image compression, for example. But with the field of compressive sensing, people ask the question, maybe we can actually reduce the number of samples that we collect in the first place. We can simplify the data acquisition process, take fewer samples, and then if we want to see what's going on in between them, we might have some way of filling in the blanks. And the analogy I like to use there is a Sudoku puzzle. So perhaps you've seen one of these puzzles before. It's a 9x9 grid of numbers. You only get to see some of the numbers, and your job is to fill in the blanks by following the rules of the puzzle, which are that every row, every column, and every 3x3 block has to use the digits 1 through 9 exactly once. So those rules are like a model for how the full puzzle is expected to behave. And if you're good at applying those rules, you can fill in all of the blanks. And for you, there's really no information missing in the puzzle. You are like an algorithm that's taking the data that you observe and filling in all of the blanks. So in compressive sensing, people look at kind of applying that same intuitive idea for capturing data and signals. Maybe we don't need to take a large number of samples of a signal or measurements of an image. We can take a relatively small number and then use algorithms, which I won't detail right here, but use algorithms that apply the anticipated models for those signals in order to fill in the blanks of the parts that we didn't measure. Random sampling is characteristic of compressive sensing, where we take a small number of samples, and usually they're not uniformly spaced because we don't want to incur aliasing with these samples. There's also another type of characteristic sampling of compressive sensing. In contrast with random samples, where we see parts of a signal but we don't see other parts, what I'll call compressed samples today, every compressed sample actually depends on the entire signal or entire image. So an example could be like on this slide, say your first measurement, Y1, could be some weighted sum, some combination of all the pixels belonging to the image, and you might choose these weights randomly. Your second measurement could be a different randomly weighted sum of all the pixels in the image. As long as you take a total number of measurements, called M here, that's smaller than the number of pixels in the image, then you have achieved a type of compression. It may not be obvious at first glance that these sorts of measurements can be efficiently captured, but there are imaging and optical systems that have been proposed for doing compressive imaging in this way without ever physically measuring all of the pixels one by one. And before getting into modal analysis, I'll just mention more generally that there have been a number of promising directions and successes of compressive sensing to date. As I suggested, you could go below the Nyquist rate for sampling certain structured analog signals. So these ideas have been used in designing new analog to digital converters. I'll show an example in a moment from exploration seismology, where typically the data sets are very large and expensive to capture, and there's strong motivation to reduce the amount of data that you collect there. Medical imaging is another example. On the bottom of the slide is some material from Philips, where they've developed what they call a compressed sense technology that can reduce scan time in a magnetic resonance imaging system by about half, as they say, with virtually equal image quality. There's other applications in quantum information. Siemens has incorporated compressed sensing technology into MRI scanners, in this case for video captures. As they say here, rather than taking nearly 6 minutes with multiple breath holds, one of these cardiac videos can be captured within 25 seconds and allowing the patient to breathe freely. This is one of the examples they provide with a standard free breathing scan on the left and a compressed sensing free breathing scan on the right. ConocoPhillips is employing compressed sensing technology. As they say here, they're planning to undertake a 3-dimensional marine seismic survey using these ideas, which can acquire similar information to conventional surveys, but with fewer samples and in less time. So that's just a broad introduction to the theme of compressive sampling, but I want to now focus on the particular topic of today's talk, which is a slight departure from the mathematical details of what people normally do in compressed sensing problems. But I'll focus on modal analysis, which has applications in structural health monitoring. So the scenario we envision here would be monitoring something like a building or a bridge for damage or fatigue over time, which could then be used to flag such a structure for inspection or maintenance. And there's interest in using wireless sensors on such structures, which might acquire vibration data over time, perhaps transmitting this all to a central node for processing to assess the health of the structure. And we'd like to do this as efficiently as possible, while still having some guarantees about how accurately we can assess the health of the structure. So I'll give some mathematical details about what we assume and how we can kind of frame this as a compressive sensing problem. So the setup we envision would be something like this. Maybe we have a structure like a bridge with n sensors spread across that structure. And over time, each of these sensors is measuring the displacement of that sensor location. This could also be done with velocity or acceleration, but I'll just assume displacement here. And over time, we would sample these displacement signals. We'll get to compression in a minute, but for now, let's suppose that we sample these signals uniformly in time, maybe at a total of m different time instants. So we could then stack all of the data that we capture into a matrix that we'll call X. That'll be kind of our object of interest. We'll call this the data matrix. We'll assume we collected these samples in time fast enough to satisfy the Nyquist criterion. So that gives us this n by m data matrix. N is the number of sensors, m is the number of uniform time samples. We'll get to compression again in a minute, but what will we do with this matrix? So we'll perform modal analysis, that is to estimate the modal frequencies and or the mode shapes of the structure. And we would like to have some provable accuracy on how well we can extract these parameters of interest. I'll show what we mean by that in just a second. Meanwhile, though, in the spirit of compressive sensing, we would like to minimize the sampling and communication burdens of capturing this data matrix, potentially by using random sampling or compressed sampling of the data matrix. So we'll get to those ideas in just a minute. So when we say we want to extract the modal frequencies and the modal parameters, here's what we mean by that. So under if we model this structure with a differential equation using the second order equations of motion for an n degree of freedom system, if we assume that there's no damping in the structure and that it's undergoing free vibration, then we can write the solution to the equations of motion in this form. We could stack all of the time varying displacement signals into a vector we'll call x of t. And at any time instant, x of t could then be written as a weighted sum or a superposition of these characteristic mode shapes. We'll call phi 1, phi 2 up to phi k, where k is the number of active modes in the structure. But the weights on these modes are changing over time. And if we assume we've captured signals in their analytic form, then we can write the modulating weights as this time varying complex sinusoids with frequencies f1, f2 up to fk, which we also don't know, but we would like to learn them from the data. And potentially there could be amplitudes a1 up to ak as well. But the main things we'd like to extract from the data are the mode shapes phi and the modal frequencies f. Here's an example of what those might look like. This was using real data captured from a bridge in Ypsilanti, Michigan. This bridge had 18 vibration sensors on it. You can see an example of some of the time varying signals up here. And from that data was extracted 3 dominant modes having these 3 shapes that you see below. So this tells us that this bridge has a bending mode, which is oscillating with a frequency of about 2.4 hertz, twisting mode, which is oscillating slightly faster, 2.8 hertz, and then a third mode, which is about 4 times faster than the other ones. So at any time instant, then, this means that the actual displacement profile of the bridge is a combination of these 3 shapes, but the weights on those shapes are changing over time, some relatively slowly, some quickly. And we don't know any of these shapes or frequencies, but they're what we would like to extract from the raw data that we capture. So there are many techniques that have been proposed for modal analysis, and in a short talk like this, I don't have time to cover all of them. So I want to highlight two techniques, one very simple and classical, one more modern, coming from the compressive sensing community, both of which, though, are amenable to the random sampling and compression that we're inspired to explore here. So the classical technique is the proper orthogonal decomposition, or POD. It's a very simple technique. It basically says you take this data matrix X and you apply what's called the SVD to the data matrix. It's a technique from linear algebra, which just factors X into a product of other structured matrices. The first of those contains what are called the left singular vectors of the data. And under certain assumptions on the structure, these left singular vectors of the data matrix can actually be an approximation to the true mode shapes. I'll show a little more theory for that in just a second. But simply by doing a POD on the data matrix, you can get an estimate of the mode shapes. Unfortunately, it does not give you an estimate of the modal frequencies, but we'll talk about another technique that does. And that brings me to the second technique, so atomic norm minimization. This is the more modern approach, which has come out of the greater compressive sensing community. And it comes from the following observation, that if we think about this data matrix X, and we go back to those equations of motion that I showed earlier, it follows that X can actually be written in a very structured way as a combination of rank 1 matrices. Each rank 1 matrix is formed as an outer product of that unknown characteristic mode shape phi k times a sinusoidal vector oscillating with the unknown frequency fk. So it's a low rank decomposition of X using rank 1 matrices whose structure actually reveals both the unknown mode shape and the unknown modal frequency. Now, we don't know those in advance. We'd like to extract them from the data, but having such a concise description of X motivates thinking about it this way. You could imagine sort of a dictionary of all possible rank 1 matrices with that structure. And you could ask, what's the most efficient way I could build up X using elements from that dictionary? That most efficient combination is called the atomic norm of X in that dictionary. And that can be formulated as an optimization problem that can be attacked or solved using tools from convex optimization, specifically semi-definite programming. All that to say, though, given X, the data matrix, or possibly a compressed version of X, we can solve an optimization problem to reveal specific estimates for the modal frequencies and the mode shapes. And in certain conditions, which we'll see in a minute, these estimates can actually be exact recovery of the mode shapes and the frequencies. And in contrast with other classical work in compressed sensing, this works even if the frequencies are so-called off-grid. We don't have to assume that they belong to a predetermined grid of possibilities. So with the time remaining, I'm just going to step through various scenarios for how we might collect the data and what do we know about how POD and atomic norm minimization might perform for recovering the mode shapes and the modal frequencies. Some of these are results that we have come up with, and some of them are from other folks in the literature, and I'll cite them as appropriate. So first, without doing any compression, just what if we have classical uniform samples of our data matrix in time? Well, for POD, as I mentioned earlier, we can approximately recover the mode shapes with an error that is comparable to some parameter epsilon. And if we want smaller epsilon, we'll need to take more samples, m. And also depends on the separation between the amplitudes. How distinct are all of the amplitudes in this modal decomposition? But more importantly is m here, the number of uniform time samples, kind of how long in time do we need to observe these vibrations? And the essential scaling I want to talk about here is that m needs to be inversely proportional to delta f, where delta f is this It's the minimum separation between any pair of the modal frequencies. If you have any pair of modal frequencies which are very close to each other, you have two modes oscillating with very similar frequencies, you actually need to observe your structure for a long amount of time in order to distinguish those two things. That's a pretty natural intuition coming from, say, classical signal processing, for example. We'll see that that shows up in a lot of these results. Another limitation of POD is that it really only works with orthonormal or orthogonal mode shapes. Some structures, you can assume that to be true, or you may be able to renormalize your data in order to achieve that. But in contrast, atomic norm minimization does not require the mode shapes to be orthogonal. In fact, it can give exact recovery of the mode shapes and the frequencies. And the requirement on M is essentially as it was above, scaling inversely with delta F. So if you have a pair of closely spaced frequencies, you need to sample for an appropriately long time. Now, with these results established, what can we say about random sampling and compression? So we'll look at a few different scenarios here. The first is, what if, over the same total time span, we know we need to observe the structure for a certain amount of time, but maybe we don't need to collect a lot of samples during that time. What if every sensor is sampling randomly, collecting just samples at the red times here and ignoring the samples in between those times? Well, as long as we sample for the same total duration, we may be able to keep a smaller number of samples M prime, which scales most importantly with K, the number of active modes. So this is a nice result that your sample complexity is really proportional to your information complexity, the number of active modes that's happening in your structure. That's true really both for POD and for atomic norm minimization. The essential number of samples you keep should scale proportionally with K, the number of active modes, times some extra log factors. That's if all sensors are sampling at the same random times. You could also imagine having sensors sample at different random times. So maybe every sensor is collecting M prime samples, but at a collection of different randomly selected times, and then they send these to the central node for running an algorithm to estimate the mode shapes. In this case, it's really not appropriate to use the POD algorithm, but the requirements for atomic norm minimization are very similar to what they were for the other type of random sampling scheme. There's a certain duration over which you need to sample the signal, but the actual number of samples you collect really scales essentially like the number of active modes there. Now, those are all random sampling ideas where we see some of the samples, but not others. We can also think about random compression techniques. If you recall the image example I showed earlier, where every measurement was a combination of all the pixels in the image, that's kind of analogous to what we're talking about here. Now we would take, let's say from sensor number 1 here, maybe it collects M total time samples, but it compresses those before it sends them to the central node. It compresses them where every output sample is a weighted random sum of all of the input samples. And that can be expressed as multiplication by a random Gaussian matrix. Maybe sensor 2 does the same thing. Each one of the sensors does the same thing to do this compression. And we can look at how many total compressed samples does each sensor need to acquire. We'll again call that M prime. And the requirements on M prime are very similar to what they were for both of the random sampling schemes, essentially scaling like K, the number of active modes, again with an additional logarithmic factor here for the atomic norm minimization. Let me demonstrate the POD method using this random temporal compression. So we go back to the data from this bridge. Again, there were 18 sensor nodes. We had 3,000 uniform time samples available from this data. And as I showed earlier, there were 3 dominant mode shapes. So the data matrix itself, if we created the entire data matrix, it would be 18 by 3,000. But then we applied random temporal compression. So we compressed it down to 18 by just 50. So at every sensor, the 3,000 samples were compressed down to 50 numbers from which we're trying to do the modal analysis. And this is a plot of the 3 mode shapes as a function of the sensor location. The blue indicates what we consider to be the ground truth, what would be acquired with full data. The black is using kind of a naive compressive sampling method, which we're not championing here, but the red is just applying the POD on that small matrix of compressed data. So instead of an 18 by 3,000 matrix, it's an 18 by 50 matrix. And the mode shapes are a very good match for the original mode shapes that would have been extracted from the uncompressed set of data. And the final compression technique I'll talk about here, in contrast to randomly compressing in time, where we are squeezing our data matrix horizontally, we can also consider random compression in space, where we're squeezing it vertically. So here you could imagine that at every time instant, somehow the sensors work together to collaboratively compress these numbers, delivering just one number to the central node. This might be achieved using certain RF communication techniques. Now, again, POD is not really appropriate, but atomic norm minimization could be used. And the total number of samples, M, that we take here still needs to scale inversely with delta F, the minimum separation between frequencies. We also need to make sure that M is at least K times N, which really is the total number of unknown parameters that we're trying to extract from the data. So it's fairly natural that that would appear there. I'll just summarize 2 kind of takeaway messages here. The first one about the benefits of compression. Again, when delta F, the minimum separation between mode frequencies, is small, all of the methods we've talked about do require sampling over an appropriately long time span. However, during this time span, it may be possible to do sampling below the Nyquist rate using these random sampling and compression techniques. These are some results from atomic norm minimization, a scenario with 5 sensors that we synthesized, 3 different mode frequencies and mode shapes that we generated. And then we looked at all of these compressed techniques. Kind of Nyquist sampling would require about 100 samples per sensor. We compressed down to 20 samples per sensor. And we did that using either asynchronous or synchronous random sampling or temporal or spatial random compression. All of these techniques worked well in a majority of the trials. This is the percentage of trials in which we got perfect recovery of the frequencies and perfect recovery of the mode shapes. In contrast, uniform sampling would require a large number of samples, as I said earlier. If we just try to use a small number of uniform samples, well, we're either going to only be able to use uniform samples quickly for a short amount of time, or slowly over a longer amount of time. But that, we're either not seeing the data for long enough, or if we sample slowly over a long time span, we'll incur aliasing. And so both of these uniform techniques end up failing. The other takeaway, the required number of compressive samples per sensor scales with the information level, that is linearly with the number of active modes. This was using random temporal compression on a scenario with 10 sensors. And we see as this, what we call the sparsity, but K, the number of active modes increases, we see that the number of measurements per sensor M prime needs to also increase approximately linearly with that, as we would expect. So just to conclude, in general, having structure in signals and data can permit random and compressed sampling, hopefully with sample rates that are proportional to the really intrinsic information level in your signal. Depending on what sort of mathematical problem you're trying to solve, you may need a customized inference algorithm, either to fill in the blanks or to extract the information like modal frequencies and shapes. And among the possible techniques, atomic norm minimization is a very powerful one that in certain cases can give exact recovery. You know, in this limited time, I haven't had a chance to fully overview atomic norm minimization, but it has many capabilities, many ways of extending the model or dictionary that you're using, extensions to be robust to noise, different algorithms, and also different theoretical guarantees for recovery with atomic norm minimization. But I will stop here. Thank you again for attending, and I'll be happy to answer any questions.
Thank you so much, Professor Wakin. At this point, I want to stop the recording.